And so begins the lecture for Chapter 14 on heat. Essentially, we're going to talk about heat and how it's actually the transfer of energy. And there's three ways: conduction, convection, and radiation, that we'll talk about here. Since we're talking about energy transfer, we need to talk about where the energy comes from, so this concept of internal energy. We'll talk about calorimetry, which is related to both the specific heat and the latent heat, and solving problems is going to be kind of the main point of this chapter. So let's get started on heat. Very often we'll say that we talk about heat as if it was a property of a material, but really it's not. It's going to be essentially a form of energy. Something else to kind of keep in mind is heat is not going to be equal to temperature. It's going to be related to temperature, but it's not going to be the temperature. It's a form of energy. Energy is also related to temperature, so heat is related to temperature, but it's not going to be the temperature. Since it's energy, the unit is going to be, well, I'll be talking about joules in a little bit, but let's just talk about calories for a second. Joules and calories are both units of heat, units of energy. Essentially, 1 calorie, keep in mind it's a small c, is going to be the amount of heat that's needed, the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Something with our food labels is, they're labeled in capital C calories, which is actually a kilocalorie, or 1,000 calories, and that's the heat needed to raise 1 kilogram of water by 1 degree Celsius. And kind of as advertised on the last slide, we're not going to be working in calories or kilocalories. We're going to be working in the SI system. We'll be working in joules or kilojoules, and kind of the conversion you see is going to be right here. 4.19 joules is going to be 1 calorie, or kilojoules per kilocalorie. Since heat is actually a form of energy, what we can do is we can say, hey, let's set up an experiment where we can get some mechanical equivalent of heat, where we take this weight right here, we hook it to a pulley, and now it's got some potential energy. It's got this mass times gravity times height, and essentially if we let that weight fall down to the ground, here it's going to have no potential energy. Well, where has that energy gone? Well, what it's done is it's spun these paddle wheels around, and it's gone into the thermal energy of this container. So we could kind of pop a thermometer in there. We would see the temperature has gone up, which means that the energy inside of this jar of water has gone up. The same thing is going to be true for kinetic energy. If you're say going fairly fast on the highway, you apply your brakes, the energy is going to go into heating up your brake rotors. So now for kind of a more formal definition of heat. Heat is going to be the energy transferred from an object, or from one object to another, because of a difference in temperature. So again, heat is not going to be equal to temperature. It's going to be the energy transferred. Thinking about kind of the fact that the temperature of a gas is related to the kinetic energy of its molecules, and thinking back to that paddle wheel example from the last slide, as energy was essentially added to the system by the weight pulling on it, then these paddles were kind of smacking into all of the water molecules, essentially causing them to move faster, which is going to raise the temperature, and so it's going to be the energy added to the system. So kind of to say heat is going to be equal to the energy added, and kind of conversely to say, we could cool something off by taking energy away. So now let's introduce this concept of internal energy. Essentially, if we were to say, hey, I'm going to sum up all of the energy inside of a material, then that's going to be its internal energy. So its internal energy is going to be equal to, say, all of the kinetic energy of the molecules plus the potential energy of the molecules. Remember in the last chapter I kind of said, hey, if we have a solid material, then we can kind of pretend that we have a bunch of atoms that are bonded to one another on springs. So essentially these guys are vibrating back and forth and up and down, and so there's going to be kinetic energy because the molecules are moving. There's also going to be potential energy kind of from the springiness of the bonds. Temperature is related to only the kinetic energy, or how fast these molecules are moving. Internal energy is going to be that kinetic energy plus the potential energy from the bonds. Now suppose that we had, just for a second here, two chunks of, say, iron, and this one was at temperature 1 and this one was at temperature 2, and this guy here, let's just say that it's a little bit cooler. It's not going to be moving nearly as fast, and it's not going to be stretching the springs nearly as far. If these two guys were touching, you can kind of imagine that this temperature 1 guy kind of bumping into this guy right here, then we're going to be transferring some energy from the hot chunk of metal to the cold chunk of metal. So we're going to be transferring the energy because there's a difference in temperature here. Now for gases, we know that they're a little bit simpler and that we don't have those chemical bonds that act like springs. So we can essentially say, that the internal energy of an ideal atomic gas, essentially all of our gases will be ideal. We can say that's just simply going to be, this is the internal energy. It's related to the number of molecules that we have multiplied by their kinetic energy, because they don't have that potential energy. Kind of cue to the image from the last chapter. Now we know what this kinetic energy is in terms of temperature, and so we can write this super important equation right here, which is going to be the internal energy of the gas. So there's going to be internal energy. It's going to be 3/2. This is going to be the number of moles of the gas. This is going to be the gas constant. And this is going to be the temperature, and this temperature must be in Kelvin. That's going to give us the energy. This energy will be in joules. Since we're only talking about a gas that has one molecule in it, we're going to say that this is only going to be true for monotonic gases. If the gas is made up of molecules, then there's going to be the atomic energy as well as some energy associated with the fact that this molecule can now rotate, and there's going to be some chemical bonds in there, so there's going to be some potential energy. So we can write the internal energy of the gas is going to be 5/2 number of moles, gas constant, temperature. And again, this is going to be in joules, moles, that's just gas constant, and that must be in Kelvin. And essentially this 5/2 says, hey, there's going to be some, not just the energy associated with the kinetic energy, but with this rotation and vibrational energy as well. This is going to be true for diatomic gases. Now that we've talked about internal energy, let's talk about how we can change the internal energy. We're essentially going to be adding heat. So here's kind of my system, and it's got some internal energy, and I say, hey, I want to change this internal energy. So what I'm going to do is I'm going to dump some heat into this system. What we can do is we're going to say, okay, well, this heat here is going to be given the symbol Q, and it's going to be measured in joules because it is an energy. That's going to be related to how massive the system is, some constant, which is a characteristic of the material, it's called the specific heat, as well as how much it changes its temperature by. What this specific heat kind of is, it's kind of like a thermal inertia. I mean, imagine if we, say, poured 1,000 joules of heat into a system and it had some mass that you can't change. If this specific heat was very large, then the temperature change is going to be fairly small. If this specific heat was fairly small, then the temperature change must be very large. Some values for this specific heat, which is again kind of a thermal inertia, are given in this table. Very typically we're going to work in the one that has joules here. You can kind of see different substances are going to have different thermal inertias. So aluminum is going to be slightly different than copper, which is going to be different than lead. And we're going to talk about water quite a bit. We can see that water has a very large value for a specific heat, so it has a very large thermal inertia, if you will. And this is going to be a fairly important equation. We're going to be using it quite a bit in this chapter. Make sure that we're kind of good to go on it. Again, Q is energy in joules, M is mass, hopefully in kilograms, C is some constant that you either look up or you're given. And this change in temperature is going to be the change in temperature, which could either be in Kelvin or it could also be in Celsius. Remember in the last chapter I said that a change in temperature is going to be the same. Now, the last slide spoke to the specific heat or thermal inertia of liquids and solids. Gases are just a little bit more complicated because it could be measured with either constant pressure, Cp, or constant volume, Cv. most typically we're going to be working with this one right here, and there's actually a very simple relationship that says Cp, specific heat at constant pressure, is going to be equal to specific heat at a constant volume plus that ideal gas constant R, which was like 8.315. Kind of a table here for a specific heat of gases at constant pressure and constant volume. This is more something we're going to use in Chapter 15 than in Chapter 14. So now let's move on to the most important topic that we're going to be covering in this chapter, and that's of calorimetry, and just get some basic definitions out of the way. We can have closed systems where we're going to have no mass entering or leaving, but energy may be exchanged. So you can kind of think of something that's in thermal contact with one another, exchanging energy but not exchanging mass. We can talk about an open system where mass is going to be transferred between two objects. Very tough. Even my calculus students won't be looking at this type of problem. The type of system we'll be working with here is going to be isolated systems, where it's going to be a closed system where no energy is transferred to the environment. So it's going to be a system where mass is going to be touching, and no energy is going to leave the system. So for example, suppose I had a bucket of water and I had some ice cubes, and I kind of dunked the ice cubes into the water and said, well, what's going to happen at the end of the day? Well, I can say that the energy over here must be equal to the energy over there. So we can say the energy that leaves one part of the system is going to be the energy that's gained by the other part of the system. So here we're going to have the water losing some energy, cooling down. It's going to be giving it to the ice. Now remember that we can say that Q energy is going to be equal to mass times specific heat times change in temperature. And this temperature, delta T, is going to be some temperature final minus temperature initial. You can kind of see whether an object has a higher or lower final temperature versus initial temperature. This energy can be either negative or positive. We could also say that the heat loss is going to be equal to the heat gained. So Q1 must be equal to Q2. But keep in mind the key word here is lost, so this energy is going to be negative. I like to write this personally as the sum of Q's must be equal to 0. No heat can enter or leave the system, and so Q1 plus Q2 are going to be equal to 0. Therefore Q1 must be equal to negative Q2. So kind of what calorimetry is going to look like is we're going to have an isolated system. So we're going to say take some water, put it in a beaker, and put it in a nice insulating jacket, which is typically styrofoam in the laboratory or can get more fancy in other applications. And we say, hey, we're going to stick a thermometer in this water and we can measure how much the temperature is going to change. We just have a little stir to keep the water agitated. It's not really adding any energy to the system, we'll say. And we can say, hey, I'm going to take a hot piece of iron and kind of dunk that guy into the water. So we're going to say, hey, we're going to have an isolated system, and so we can say that the sum of the Q's is going to be equal to 0. So here we have the iron that has some energy associated with it, plus the water. And suppose I'm interested in the specific heat of the iron, I can say that the heat lost by the iron is going to be negative heat gained by the water. So mass times specific heat of iron times the change in temperature of the iron is going to be equal to the mass of the water, make sure that's iron, specific heat of water, which we know, and change in temperature of the water, which we can measure with this thermometer right here. So we typically would know the mass, specific heat, and change in temperature of the water. We would also know the change in temperature of the iron. We would know what temperature we initially put it in. At the end of the day, it's going to be in equilibrium with the water, and so the temperature of the iron final is going to be equal to the temperature of the water final. So we know with the temperature change, we know how massive it is, so we could go ahead and calculate the specific heat, in this case of the sample.